Hi everybody, this is Mrs. T for Mrs. T's Chem Talk AP Chem. This is going to be a video on using the sum formulas to find delta H, delta G, or delta S of a reaction and how those different formulas are going to interact. So the first thing to note, we learned this formula a while ago already in the beginning or in the middle of chapter 6 in our textbook. The delta H, the standard delta H of a reaction is equal to the sum. Remember that this is the letter sigma, which means sum of the heats of formation, the standard heats of formation of the products, minus the sum of the standard heats of formation of the reactants. Now remember, for each of these, we're going to take the heat of formation of the individual reactant or the heat of formation of the individual product and multiply by its coefficient in the reaction. We're going to add up all the ones for the products, add up all the ones for the reactants, and then do products minus reactants. We have similar formulas for delta S and delta G. Remember that delta S is entropy change. Again, we're going to do the standard entropy of the products minus the entropy of the reactants. And for delta G, which is the Gibbs free energy, we're just going to do the Gibbs free energy of formation of the products minus the Gibbs free energy of formation of the reactants. Formulas are used the same way. You're just going to look up either the H heat of formation for the delta H sum formula, the standard entropies for the standard entropy formula, or the Gibbs free energy of formation for the delta G formula. We can use any of these formulas like that, or we can find the delta H for the reaction and find the delta S for the reaction and plug it into this formula, which is the Gibbs free energy formula, which is delta G equals delta H minus T delta S. Just a little note for this particular formula is that delta S is usually given in joules, well, joules per Kelvin, whereas delta H is usually given in kilojoules. So we usually are going to need to convert the delta S to kilojoules before we can use them together in the delta G formula. So now, when we are calculating the delta S, delta H, delta S, and delta G, if let's say we have a reaction that looks like this, and they want to know the delta H, the delta S, and the delta G, and all they give us is this data. So what we should notice is that we have heat of formation data and entropy data, which means for our products and our reactants, which means we're going to use the sum formula to get the heat, the delta H of the reaction. We're going to use the sum formula to get the delta S of the reaction, and then we're going to plug all that information into the delta G formula of delta G equals delta H minus T delta S. Okay, but notice again, this is in joules per Kelvin mole. This is in kilojoules per mole. So we're going to have to convert the delta S into kilojoules per mole before we can use it. Look at the reaction and identify our reactants and products so that we can find the delta H using the sum formula. The sum formula, remember, says that we take the sum of the heats of formations of the products and subtract the sum of the heats of formation of the reactants. Remember, this letter sigma means sum in math. Our reactants are the species before the arrow. Our product is what's after the arrow. So be very careful because the SO2 is here, the O2 is here, but SO3 is in the middle, and this is a product. Remember that heats of formations of elements are 0. We're going to multiply that by the coefficient, which is 1, which keeps it as 0. And then the SO2's heat of formation, we're going to multiply by a 2 because of this coefficient of 2. So 2 times negative 297. So when we set that up, 2 times the heat of formation of our product, because it had a coefficient of 2. And we're going to subtract the sum of 2 times the heat of formation of SO2 plus 1 times the heat of formation of oxygen. Make sure you have your calculators out. Make sure you're doing this along with me. That gives us a negative 792 minus negative 594. You can just put that into the calculator just like that, or you can cross out your negatives and make it addition. That's going to give us a delta H for this reaction of negative 198 kilojoules per mole of reaction. I put it as per mole of reaction because now this is according to the coefficients that are given here. The next thing we want to do is use the same formula to find the delta S. Remember that our delta S will come out in joules per Kelvin mole reaction, so we're going to have to go from joules to kilojoules. The reactants are still the species before the arrow. The products are after the arrow. We're going to use the sum formula. It looks very similar. It's the entropies of the products minus the entropies of the reactants. We're going to remember that SO3 is a product. Its entropy now gets multiplied by 2. SO2 is a reactant. Its entropy gets multiplied by 2. Oxygen is a reactant. Its entropy gets multiplied by the understood coefficient of 1. When we plug in the numbers, SO3, we do 2 times 257 because it was our product. Coefficient of 2 for the SO2, 2 times 248. And we're going to add coefficient of 1 times 205. Pause if you need to do that with your calculator. We wind up with 514 minus 701. Remember, our unit will come out in joules per Kelvin for mole reaction. And we wind up with a negative delta S, which means that the entropy for this reaction is decreasing. We wind up with negative 187 joules per Kelvin mole reaction. Because 2 moles of gas plus 1 mole of gas combine, those 3 moles of gas combine to make only 2 moles of gas, we would expect, since the moles of gas decrease, we would expect a negative change in entropy. We're getting more organized, less gas is present. Let's take that joules per Kelvin mole reaction and we're going to convert it into kilojoules. Remember that kilojoules, there are 1,000 joules in a kilojoule, so we're going to either divide by 1,000 or move the decimal point back 3 places, and it comes out to negative 0.187 kilojoules per Kelvin mole reaction. We're going to take those pieces of information. Sorry, I have some numbers at the bottom of the screen. I don't know why those are there. We're going to take this information and we're going to plug it into the delta G formula. So we're going to plug in our negative 198 kilojoules per mole reaction. We're going to plug in our negative 0.187 kilojoules per Kelvin mole reaction into our formula, and we're going to wind up with negative 198 kilojoules per mole reaction minus, remember it said it was at 25 degrees Celsius, so that's our 298 Kelvin, which is our T, times our delta S, which was negative 0.187 kilojoules per Kelvin mole reaction. When we do those pieces of math, we wind up with negative 198 minus a negative 56. So again, you can go back and pause and make sure you do that on your calculator, make sure you get the same numbers. But this is just the negative 198 pulled down, minus, and then 298 times negative 0.187 came out to negative 56. Because we are subtracting, I did round to significant figures here. That's why this is a 56 and not the number that came out of the calculator. When we do the math there, our delta G comes out to negative 142 kilojoules per mole reaction, negative 198 minus a minus 56, which is the same thing as saying negative 198 plus 56. We wind up with a negative delta G, negative 142 kilojoules per mole reaction, which means that this reaction is favored. This reaction is spontaneous, if you use that terminology, or it is thermodynamically favored, meaning that we are increasing the entropy of the universe because of this negative Gibbs free energy value, and this is the indication that this reaction can proceed from reactants to products without help. Also get delta G just straight using the sum formula. So this would be an example of a different kind of information that could be given. So in this particular question, methanol is a high-octane fuel used in high-performance racing engines. Calculate the delta G for the following reaction. The following energies of formation are provided, and they're giving you Gibbs free energies of formation for these different substances. we're going to take these different Gibbs free energies and we're going to use the sum formula to find delta G. When we use the sum formula, again, we're going to do products minus reactants. We always multiply by the coefficients. So I'm going to identify that these two are my reactants. These two are my products. This has a coefficient of 2. This has a coefficient of 3. Carbon dioxide has a coefficient of 2. And H2O has a coefficient of 4. That means we're going to multiply each of those numbers by those coefficients in our sum formula. So we're going to wind up with 4 for the H2O times negative 229 plus 2 for the CO2 times negative 394. We're going to add those two things together. Then we're going to subtract for the reactants. 3 for the O2, which is times 0, so we don't have to worry about that one, luckily. And then it's going to be a 2 for the methanol times its delta G of formation of negative 163. We're going to add all that together. Wind up with a negative 1704 minus a negative 326. So what we're really going to do is make that a positive. So we get negative 1704, right? Negative, negative plus a 326, and our answer comes out to 1,378 kilojoules per mole reaction, and that's negative. So again, negative delta G means that this will be a favorable reaction, meaning that the reaction will be thermodynamically favored. It should proceed to products because of that. So thank you for watching. This was a video on using the sum formulas and using the delta G formula in different situations. If you have any questions, please come find me at school for extra help. If you're not one of my students, please feel free to explore my YouTube channel, Mrs. T Chem Talk, to see if there's anything else that could help you there. Thanks a lot.